The ground trembles, rhythmically shuddering under footsteps that rival a tectonic shift. Rising above the ancient conifers is a silhouette that blocks the sun, a biological skyscraper, challenging gravity itself. How does a heart pump blood 4 stories high without bursting? This creature is nature's ultimate hydraulic experiment. This is not a monster. This was a living animal, fighting for survival. In this dossier, we will move beyond the bones to resurrect its world. This is Brachiosaurus, the living dossier. Let's journey back to a world where the past is reborn. To truly grasp the scale of this creature, we must first examine its biological blueprint. Its name, Brachiosaurus, translates literally to arm lizard. This isn't just a label, it is the key to its posture. Unlike most sauropods, whose bodies were level with the ground, this animal was built on a steep incline. As our skeletal reconstruction demonstrates, its forelimbs were significantly longer than its hind legs, creating that iconic, giraffe-like silhouette that defines the species. Roaming the prehistoric floodplains of the Morrison Formation in North America during the late Jurassic, approximately 154 million years ago, this colossus was a master of verticality. Estimates suggest a length of roughly 25 meters and a staggering height of 13 meters or more. Weighing in at anywhere from 30 to 50 tons, it was a specialized high browser, an herbivore designed to exploit a canopy niche that no other terrestrial animal could reach. It wasn't just big, it was an architectural anomaly. To understand the Brachiosaurus, we must step into the landscape of the Morrison Formation. Imagine a vast, semi-arid floodplain marked by distinct wet and dry seasons, dominated not by flowering plants which had yet to take over the world, but by ancient conifers, tree ferns, and ginkgos. This was the Serengeti of the Jurassic, a crowded ecosystem teeming with the largest land animals to ever walk the earth. A critical question arises: how could this environment support so many multi-ton giants simultaneously? The answer lies in a concept paleontologists call niche partitioning. As our layered ecosystem model illustrates, the herbivores of the Morrison did not compete for the same meal. They divided the world vertically. While the whip-tailed Diplodocus and the robust Apatosaurus swept the ground level like biological lawnmowers, grazing on ferns and low-lying vegetation, the Brachiosaurus occupied the penthouse suite. Its vertical neck allowed it to strip foliage from heights of 9 to 13 meters, a feeding zone completely inaccessible to its neighbors. It had exclusive access to the caloric riches of the upper canopy. Here, it feasted on the tough, needle-like leaves of conifers and cycads. It didn't chew. Its spoon-shaped teeth were designed for raking and cropping, swallowing massive amounts of vegetation, whole to be processed by a formidable gut fermentation system. While predators like Allosaurus and Ceratosaurus stalked the shadows of the undergrowth, the head of a fully grown Brachiosaurus floated safely above the danger, surveying a world that belonged entirely to it. It was not just living in the ecosystem, it was the master of the vertical world. When we deconstruct the anatomy of the Brachiosaurus, we are faced with a biological riddle. How does physics allow this animal to exist? The most obvious feature, that 13-meter neck, should theoretically be too heavy to lift. If these cervical vertebrae were solid bone, like the spine of a mammal, the animal would collapse under its own weight. However, examining the fossilized cross-sections reveals a marvel of natural engineering. The vertebrae are not solid. They are highly pneumatized, riddled with air pockets and hollows, much like the honeycomb structure found in modern birds. As our biomechanical model shows, this reduced the weight of the neck by nearly 60% without sacrificing structural integrity. This wasn't just a skeleton. It was a latticework frame, supported by a complex system of ligaments acting as tension cables, holding the neck upright with minimal muscular effort. But the structural engineering is secondary to the true miracle, the plumbing. The Brachiosaurus faced a hydrostatic challenge no other terrestrial animal has ever conquered. To pump oxygenated blood from the chest cavity vertically up to the brain, a distance of nearly 4 stories, requires pressure that would rupture the blood vessels of any modern animal. Paleontologists and cardiologists estimate that the Brachiosaurus required a systolic blood pressure of over 400 millimeters of mercury, more than 3 times that of a healthy human, and significantly higher than even a giraffe. To generate this force, the heart itself had to be a titan. We hypothesize a 4-chambered engine weighing roughly 200 to 400 kilograms, beating with the power of a hydraulic ram. Yet, this high-pressure system creates a deadly risk. What happens when the giant lowers its head to drink? Gravity would instantly reverse its effect, sending a catastrophic rush of blood accelerating down towards the brain, potentially causing a stroke or blowing out the delicate capillaries of the eyes and nose. To survive a simple sip of water, the Brachiosaurus likely possessed a sophisticated network of safety valves and muscular sphincters within the neck arteries. These would act like check valves in high-performance plumbing, clamping down to regulate flow and dampen the pressure spike before it reached the cranium. Furthermore, a specialized mesh of blood vessels at the base of the brain, similar to the rete mirabile found in giraffes, may have acted as a sponge, absorbing the excess pressure. This animal was not just big, it was a walking, breathing, high-pressure fortress of biological engineering. Maintaining such a massive biological machine comes with a staggering metabolic cost. Survival for a Brachiosaurus was fundamentally a game of thermodynamics. To fuel a body of this magnitude, the animal had to function as a living, walking fermentation factory. We estimate they spent nearly every waking hour stripping branches, consuming hundreds of kilograms of plant matter daily. Once swallowed, this vegetation sat in a massive gut system, slowly breaking down to release the energy required to keep that titanic heart beating. But size provided more than just digestive efficiency. It was the ultimate shield. In the late Jurassic, the Morrison Formation was prowled by some of the most formidable carnivores in history, including the apex predator, Allosaurus, and the massive Torvosaurus. Against smaller prey, an Allosaurus was a lethal surgical instrument, but against a fully grown, 50-ton Brachiosaurus, the equation changed entirely. As our size comparison illustrates, a solitary Allosaurus stood little chance against a healthy adult. The predator would be dwarfed, barely reaching the herbivore's shoulder. For a Brachiosaurus, defense was not about agility or sharp claws. It was about brute force physics. Its front legs were like architectural columns. A single, calculated stomp from a forelimb carried enough kinetic energy to shatter the ribs of an attacker, ending a hunt instantly. The true danger lay in youth. The fossil record suggests a high mortality rate for juveniles. Before they reached their invulnerable size, young Brachiosaurus were on the menu. They had to grow incredibly fast, racing against time to reach that critical mass where they became too large to kill. For the adults, however, life was relatively peaceful. They were moving fortresses, safe in the knowledge that they had simply outgrown the food chain. One of the most persistent myths in paleontology portrays the Brachiosaurus as a sluggish, semi-aquatic beast, submerged in deep lakes, with only its head poking above the surface like a giant snorkel. For decades, early scientists believed that an animal of this magnitude simply could not support its own weight on land. They argued that it needed the buoyancy of water to survive. Today, we know this image is not just wrong. It is physically impossible. If a Brachiosaurus were to submerge its body fully to use its neck as a snorkel, the physics of water pressure would turn fatal. As our hydrostatic simulation demonstrates, the pressure exerted by the water on the chest cavity at that depth would be immense. The animal's ribcage would be compressed so tightly that the muscles required to expand the lungs would fail. It wouldn't be able to draw a breath. It would suffocate, crushed by the very water supposed to support it. Furthermore, the anatomy of the limbs tells a strictly terrestrial story. Their feet were not spreading, snowshoe-like pads designed for soft mud. They were compact, vertical columns with hoof-like claws, engineered for efficient weight-bearing on firm, dry ground. The placement of the nostrils high on the skull, once cited as evidence for a snorkel, is now understood to be related to a resonance chamber for producing low-frequency calls. These were not swamp monsters hiding in the murky depths. They were majestic, high-walking titans of the dry plains. The Brachiosaurus remains one of the most spectacular achievements of biological engineering in Earth's history. It was a creature that pushed the absolute limits of physiology, solving complex problems of fluid dynamics and structural load millions of years before humans laid a single brick. From a skeleton built of air and bone to a cardiovascular system capable of conquering gravity, it defines the majesty of the dinosaurian era. It was the living skyscraper of the Jurassic, a gentle giant that looked down upon a dangerous world with absolute dominance. What feature of the Brachiosaurus impresses you the most? Was it the colossal heart required to pump blood to the sky, or the pneumatic skeleton that made such size possible? Comment below with the dinosaur you want us to create a dossier for next. And don't forget to like and subscribe to join our journey back to the lost world.